ICMP, A World Beyond Pain. My name is Jessica Gallis-Sands, and today's featured speaker is Andrew Laman, Certified Instructor and Course Contributor of SEC 503, who will be moderating today's webcast. If during the webcast you have any questions for our presenter, please enter them into the questions window located on the GoToWebinar interface at any time. Please note that this webcast is being recorded, and a copy of the slides and recording of this webcast will be made available for viewing later today and can be found on the SANS registration page. And with that, I'd like to hand the webcast over to Andrew.
Thank you, Jessica. Hopefully everybody can hear me okay. Everything looks good on the audio in the presentation and you guys can see the slide. Welcome everyone. Thank you for joining me in our session today on ICMP. We're going to kind of dive into ICMP. My name is Andy Laman, and yes, I am addicted to packets. I've been working with packets now for, 30 years. Okay, that sounds old. Forget that part. I've had the opportunity to work in many different roles within IT, anything from the help desk up through infrastructure teams with sysadmins and storage and networking, through security teams, and spent a lot of time between actual engineering roles and leadership roles. And to be honest, the ability to read and understand packets and traffic and be able to analyze network data is basically been invaluable to me throughout my whole entire career across any of the roles that I've actually worked in. But I'm probably biased, and we're not here to talk about me. That's kind of boring. So let's talk about ICMP, or Internet Control Messaging Protocol. ICMP is a kind of unique protocol in that it actually rides in IP, but is not really a transport layer protocol. It actually doesn't transport any kind of application data like you would think with TCP or UDP or some of the other protocols. It is assigned the IP protocol number of 1 for ICMP version 4, and for ICMP version 6, it is actually protocol number 58. ICMP's role is to report errors in processing packets. Its job is to tell the sender or some device along the network path, depending on what the error message is, that a UDP port isn't available, or a particular protocol isn't working or listening on a remote system. Or maybe the packet itself is kind of too big to cross across the network and needs to be fragmented, but the do not fragment flag or something is set in the packet itself. So it's there to kind of give errors so the network can do something about that, whether it's to stop trying to connect to that port, or fragment the packet, or adjust itself to ensure the transmission and continued operation of the network. It does not report errors that are not really to do with the actual service. It's like the network circuit is down. It's not going to know that your network circuit's down or you had a router failure. That's not the role of ICMP. It's about errors in processing the packets or the datagrams themselves. It is actually also used for simple message exchanges, like with ping, and we'll look at that specifically here right in the next section. It has a very simple header. So if you look at the ICMP header, it has a 1-byte type field and a 1-byte code field, followed by a 2-byte checksum. The next 4 bytes of the ICMP header are dependent on the type and the code. Now, the type and the code are just numerical numbers to determine what type of message it is, and we'll look at a lot of different examples of those. So it depends on what type of type and code, or what type of error message or message exchange message it is. That depends on the last 4 bytes of the ICMP header. So it's a fixed 8-byte ICMP header with 4 of those bytes that may or may not be used. And then it has a particular payload. And again, that payload is kind of dependent on the type in the code. The checksum is a 16-bit or 2-byte field that covers the ICMP header and payload in ICMP version 4, which we're mostly going to talk about. It was rewritten with ICMP version 6 for those that are interested to actually include a pseudo header from the IP header. But we're not going to cover ICMP v6 as part of this talk. We just will run out of time. The let's see, the piece around the checksum is that if you actually go to read the RFC, it says it's actually a ones complement of the header and the payload. And if you actually go to do the math, it's actually a twos complement math, but you don't need to kind of do that manual checksum. I mean, we've got tons of tools that'll do it for us. It can be used for discovering and mapping for our networking teams, and that's a huge piece of it, right? We can use Traceroute, or we can use service discovery type of tools to find our servers listening on particular ports. What are our routers within our environment using like TTL with Traceroute? Well, I'll show you an example of that. What hosts are alive? Do they respond in some particular way? And all of those are very valid things that your sysadmins, networking, infrastructure team, application teams, even users may use. But they can also be used for less than good reasons, right? If somebody wants to try and map your environment, they can use ICMP tools to do some sort of discovery or mapping of your environment, or figure out what services your servers are listening to. Some sort of kind of mapping, scanning type of discovery process to get the lay of the land about your environment. So it can be used for that. And then we're actually going to also look at some more nefarious ways that it could be used, for example, with command and control traffic. ICMP is got a lot of uses around covert tunnels and maybe even doing data exfiltration. And we will look at some examples of that. But to do that, what we need to do is we need to actually figure out what is normal. And that's one of the things that I really, really like about researching and, understanding and working with packets is if I can figure out what is normal when I am hunting or looking through an environment to find bad. And that's one of the things that I actually like to do. When I go into an environment, I'm trying to be less dependent on alerting, right? We've all got alert systems, whether it's our IDSs or our IPSs or our firewalls or our endpoint protection devices, our antivirus, or, whatever they happen to be, they all kind of alert and tell us about bad or suspicious things when it sees it. And I actually like that, and those are really important, but I like to try and be more data-driven myself. I always go in assuming that the environment is compromised. Today, the network is compromised. I have to prove to myself that it is not compromised. So I purposely always assume that when I start researching, when I start looking at traffic, when I start looking at logs, this environment's compromised, my network is compromised. I have got to prove to myself that this is not a compromised environment. And in order to do that, I need to understand what is normal so I can look for abnormal type of behaviors. And when I understand what those abnormals are, then I can research those to find suspicious things and determine, oh, it's benign because it's something, or maybe this is malicious and I've proved to myself that the environment is actually compromised. So to do that, we're going to actually look at how ICMP kind of normally works in the environment and then try to compare that to some abnormal behaviors to better our defenses of our environments. So we're going to start with ICMP echo request and echo reply. Echo request, aka ping, and the reply, ping reply, or however you want to call that. Echo request is a type 8 code 0, and echo reply is a type 0 code 0. They are using those 4 extra bytes in the ICMP header, and so the 0 byte is the type, the 1 byte offset is the code, and then the 2 and 3 byte offsets are the checksums, and then the next 2 bytes are an ICMP identifier. And then the following 2 bytes after that are a sequence number. Now, how I learned this works is that when a system sends a type 8 code 0, it sets an identifier and a sequence number for that particular ping message or that particular ICMP echo request message. Reading the RFC and looking at how this stuff works, what is intended to happen is that when the responding system gets that echo request, that type 8 code 0, it's supposed to change the type code to 0, switch the source and destination IP addresses, right, because it's got to get sent back, update the checksum, and everything else is supposed to stay identical when that packet goes back. That is my interpretation, and that is how the RFC kind of reads for echo request and echo reply. The payload is dependent kind of on the operating system, and we'll look at some of examples of that. But I want to kind of point out the behavior around the ID and sequence number. So for me, the ID and sequence number was always, if I started a ping session with a particular IP address, so let's say I'm 192.168.1.1 and I'm pinging 8.8.8.8, right? Hi Google. And that's a particular ID, and my first ping packet that I send would be sequence number, let's say 1. And then I'm using that same ID, and when I send a second one, the next sequence number would be 2. So the sequence number would increment for each one that I sent to that particular IP address. And then at that point, when I get an echo reply, I could correlate those to say, oh yeah, this ID with this sequence number, I got a response to that. And you can see the little ticks on your ping command as you send these packets. That's how I kind of interpreted in my head about how that works. If I started another ping session with a different host, I would get another ID, another ICMP identifier, and then the sequence number would increase for that. Kind of that kind of same behavior about how that kind of works. So let's see if that kind of model about how I learned is actually what happens. So here is a Linux ping. This is out of Wireshark, and you can see in the kind of list section, that middle area where I have the red arrows, this ping packet has a type 8 code 0. Yay, right? It's the right type and code for an ICMP ping. And then Wireshark actually does something interesting. It actually, for the ID and sequence number field, it represents that both in big endian and little endian formats. That's what the BE and the LE are in the parentheses. And that just has to do with how the byte order is done. So big endian is what we will reference. It's network byte order, and it's how most operating systems you're probably ever going to work on are going to show it, but it actually shows it to you in little endian as well. And if you look at like the ID field there, you can see that the big endian, the 4178, if you switch those to little endian, the lower order byte is first, so it looks like it's 7841. So just that, it's a thing that with how Wireshark helps us interpret the data, it's not really important for us other than just realize you've got to pick one. We're picking the big endian, especially because all of the operating systems we're looking at use network byte order or big endian format. And you can kind of confirm that by looking at the sequence number, which is 1, which is the big endian format there for the sequence number. Now, you'll see also with this Linux payload and a lot of different versions of Linux, there is a timestamp. That's actually not technically part of the ICMP header. It's 8 bytes, and it's actually part of the data. Wireshark helps separate it out so you can see it, but it should technically be within that data section. And then you can, if you look at it kind of closely, you can actually see that there's a pattern there. If you look, you can actually see the data starts incrementing with hex 10, hex 11, hex 12, hex 13. It's incrementing hex characters. And if you look kind of where the payload there, once we get to ASCII representable characters like the exclamation point, and then if you kind of follow along when we get to hex 30, which is the number 0, you will see 30, 31, which is the 1, 2, 3, 4, 5, 6, 7, and the incrementing numbers there. So the Linux payload is 56 bytes. That's the 48 bytes in length of the incrementing characters there, plus that timestamp. And that's a very consistent payload for Linux packets. If we look at it, so here's just, I've sent 2 pings, and you can see that the first ping to 8.8.8 has the ID of 16760 with the sequence number of 1. And then you can see about a second later, again, it's roughly, ping, ping, about 1 a second, you will see that same ID, the 16760 with the sequence number of 2. And then you'll see the sequence number of 3, and kind of follows along kind of how we expected it to go. You can then also see when I started the second ping, the upper right-hand corner, you will see that it has a different ID, 16761. And you will see it increments with sequence number 1 and sequence number 2 and sequence number 3. And you can follow along with the replies as they come back. So you'll see this, the request and the replies, and each of those go about 1 second apart. So that's very kind of similar to what we expected. Let's see what Windows does. So this is Windows 10. So very, very similar. We have got our type 8, our code 0. We have our ID and our sequence number. Again, we will use the BE or the Big Endian format, our layout for that. And you can see that the ID is 1, and in this case, the sequence number is 5. Again, very, very similar, very consistent to what we expect to see out of a Windows ping. You'll also see that the Windows payload is 32 bytes versus the Linux of 56 bytes, and it does not have a timestamp in it. It actually starts immediately with the lowercase a, or hex 61, and it goes from A to W, all lowercase, and then it switches back over, so that's hex 61 to 77, and then it switched back over to A lowercase again through I. Now, I have no idea why it goes from A to W and then switches back over and goes from A to I. I read, oh gosh, a long time ago, and I cannot find the gentleman who actually wrote the article. I think he had pulled the source code or something, and there was something around however the code was written, it was easier or the way it worked. Anyway, I can't find that again on the explicit reason why they did that, but he seemed to believe that it had something to do with however the ping program itself worked. If we take this then and we look at how it works in package, notice here again with the timing, about 1 a second. Notice the length, right? So the length in these, this is using TCP dump to show this, and this length is the IP payload length, which would be the ICMP header plus the data. So that's an 8-byte ICMP header plus the 32 bytes of A through W and then A through I. So that gives us our 40-byte length, which is at the end of all of these. And you can see the ID of 1 and it increments. There's 5 and 6 and 7. But if you come down to 3/4 way down the page, I actually started a second ping. But Windows did not change the ID. It just kept using ID 1 and used additional sequence numbers. And you can see the change in the timing as well. So if you look at that 11:37:39, you can see, hey, there's a really, really quick second ping. And notice how Microsoft didn't change the ID. It just sends in and increases the number of sequence numbers that it uses. Interestingly enough, Microsoft always uses IP ID of 1, even pinging multiple different IPs, pinging 1 or 2 times, pinging 5 or 10 times, pinging multiple hosts at the same time, different IPs, whatever it happens to be, it was all ID of 1 intermixed with multiple different sequence numbers as they increment. So that was kind of interesting. I actually didn't mean to do this, or I actually, in my head, for some reason, had thought that Microsoft kind of supported just like the Linux model, where if you sent off a new ping, it would create a new ID and increment sequence numbers with it. And I was actually doing some research. This was several years ago now, and I was doing the research and real quickly had to jump on a flight. So I kicked off some ping packets and saved them and jumped on the flight. And when I was on the flight, I was looking at these going, wait a minute, I thought I kicked off a whole bunch of different ping packets, but all these have the ID of 1. And then as I kind of look through it, I'm like, wait a minute, look at the timing of all these packets. It's all intermixed. So that was kind of strange. But notice that the length is still all the same on all these. So that 32-bit payload with the 8-byte header is still the same. It just doesn't ever change that ID, which is kind of interesting. And then I was working in an environment and doing some hunting, again, trying to figure out what is bad. And I see this strange mess. Now, I've kind of highlighted it. If you look up and down, you'll see some other IPs doing the same behavior. And when I first started looking at this, I thought, wait a minute, what in the heck is going on? So notice the timing first. It's about 1 a second in groups of 3. So notice it's 34, 39, 34, 40, 41, and then there's a time period. And then it's kind of 45, and then notice it's almost 46, and then it's 47, and then there's some period of time, and then 59 and 0. And so kind of in groups of 3, these packets are being sent, okay? ID of 1 for all of them, and incrementing sequence number, but they all have different IP addresses, or there's different groups of IP addresses. Some of them repeat in there, but look at the length, 10? 10, 8-byte ICMP header, that's 2-byte payload. Ooh. So this was one of those that I was kind of like, oh no, what in the world? You get that little sinking thing in your stomach and you're like, oh man, this is going to be a long day. So we pulled this host off the network, started doing some investigating on the host, started kind of diving into what these packets are. And one of the things that jumped out at me was all of them had this same odd TTL value. Now, in this screenshot, it's a TTL of 28 or 28, but this capture point was actually 2 hops away from the actual collection point. And what we realized when we started doing an investigation on the individual host is that all of these packets had an initial TTL of 30. Now, wait a minute, TTL. Okay, so the TTL is a field in the IP header, and the TTL stands for time to live, and it helps keep packets from living on the network for infinite periods of time. So basically, your operating system picks an initial time to live value, and then how the TTL gets processed is when the first router collects gets the packet, it actually checks the checksum. If the checksum is good, it decrements the TTL value, it decrements it by 1. And if it is non-zero, it updates the checksum and then sends the packet on its way. If it gets to a 0, it then takes and it sends that packet back to the sending it sends an error message, and we'll look at that in a minute. It's kind of how Traceroute works, but it sends an error message back that says, hey, this packet time exceeded in transit, so you've got to do something else. Well, Windows systems generally have a TTL of 128. This one is 30. Now, okay, look, I get it. Some of you guys are screaming right now at the screen going, not all Windows systems are 128. Okay, you're right. Windows 95, Windows NT 351, and Windows NT 4 Service Pack, I think it was 1 to 4. Yes, they had a TTL of 32. That is still different than this one, which would be 30, and these were Windows 10 machines. This is not a normal behavior for a Windows 10 machine. So we were kind of now at the point of going, oh no, this is some sort of beaconing, this is not a good scenario, because this does not look normal for our Windows 10 systems. Well then, as we did research, we realized it was Excel. Oops, that's not good. And then not only was it Excel, we found hosts that it was happening to with Outlook and PowerPoint. And then we kind of realized it was all Office 365 applications, and that the destination hosts were all Microsoft IP addresses. So, oh, it's only Excel and PowerPoint and Outlook and all of our Office 365 applications. And after, a very short 4 months of doing a trouble ticket with Microsoft, we can confirm that this is part of their telemetry data for their Office 365 applications. The intent is to help measure latency. The reason why these packets do not look like normal packets is because they're using the footprint SDK API to generate these. So if you're an Office 365 customer, just remember that Excel and PowerPoint and Outlook and all of the Office 365 applications can now craft packets through this API. Okay, so there's another normal behavior that we need to look out on our networks. Okay, what about this one? This one, when I came across this one, I kind of really went, oh yeah, this is not good. I don't know about you, but seeing running in an ICMP echo request type 8 code 0 payload is not a very comforting feeling. It was actually kind of worrisome. I was like, oh no, this is not good. Okay, so we started doing some research, and as I first started kind of looking at this, the initial thing that jumped out at me after, you know, the kind of panic set in with this running payload is look at in the line where the time is, the 1226. If you go across, you'll see the IP, and then inside the parentheses there, you'll see the type of services first. Notice the TTL 1. Well, we kind of just talked about that TTL field. And if the packet gets to the router checks the checksum, decrements the TTL, and if it's 0, it sends an ICMP time exceeded message, type 11 code 0 message back to the sender to say, hey, TTL expired, you need to do something different with this. Well, this TTL 1 isn't going to get to my next router. So that got me thinking, oh, there's got to be more to this story. So we started doing some research, but before we kind of dive into that, let's real quick cover this ICMP time exceeded. So for ICMP time exceeded message, it's type 11 code 0, or there is a code 1. So the code 1 has to do with fragmentation. And if you receive, now it has to receive the 0-byte offset of the fragment, which basically means the first fragment. If it receives a first fragment, but not all of the rest of the IP fragments, the fragment reassembly time will exceed, and you'll get that type 11 code 1 message. But what we're looking at for this example is the type 11 code 0, which is that TTL decrement and goes down to 0, which means it can't live on the network anymore. So the router or the device that decremented the TTL to 0 generates this time exceeded message. So it is the source IP address for this message. So when it sends this message, it's telling the sending host, hey, you got to do something with this. This packet's not going to make it. Well, that's exactly how the Windows Traceroute application works. Now, this is Traceroute or TraceRT. This is not TracerT. I'm not going to pronounce it that way, and shame on you, any of you who are laughing right now. But Traceroute, so in the box on the left, Traceroute to Google, what Traceroute does is if you kind of follow along on the bottom, the blue is an ICMP echo request, and it starts with a very low TTL, in this case a 1. Well, the router is going to get it, decrement it to 0, and send back a time exceeded message. So if you look at the command prompt window, you can see that the 172.164.1 router sent back a message that said, hey, this isn't going to make it. You gotta do something different. So then Traceroute sets the TTL to 2. And so then the next router responds. And it sends 3 packets each time. That's what the 3 different columns are. It sends 3 different ones. I've only got one depicted on this page, just because it would get very colorful and a little bit busy. Not that it's not already probably a little busy. But each router, as it kind of goes through, when it sees this message, will send that time exceeded message back. Now, if you look in the command prompt, you can see kind of starting at 9, actually at 9, all the way to 19, we're seeing these kind of requests timed out. That means that the workstation isn't actually getting a response or those time exceeded messages back, which could mean that there is a firewall or infrastructure within Google's environment that kind of blocks these messages. And then ultimately, you can see when I get to the TTL of 20, I start getting a response, or the ICMP echo reply, and that's how the Traceroute application knows that it actually got a response. So keep increasing the TTL until I actually get an ICMP echo reply, and I know I made it. So now I have mapped that entire path to get to that destination IP address that I was trying to get. And then you can kind of see that in the right-hand side in the Wireshark. I've cut out about 40 packets there to try and get it to fit on the screen, and it was a bunch of those request timeout packets. But you can see that for each one of the TTLs, that the router was the responding device until you get all the way down to the packet. Let's see, which number is it? Like A94 or so, 95, and I start getting actual replies back, which means I made it to the end workstation. That's kind of how Traceroute works. Well, we go back to our running payload. Is that Microsoft's Traceroute? Maybe this is some other normal behavior. So if we pull Microsoft's Traceroute, it actually isn't the same. So Traceroute sends by default 3 packets each time, and it has a payload which is 64 bytes of zeros. Where the running, while it was a 64-byte payload, it's actually only sending 2 packets each time. So it's kind of a different behavior again. So back to the workstations, pulled the workstation, started doing some investigation, pulled the packet captures for events that kind of happened before and after this. Why did this device start sending these packets? What did the device do after sending these packets? Apparently, it's trying to map the environments through some sort of trace route because the TTLs are incrementing. But what is it trying to do? What caused it to do this? Well, as we were looking through the packet captures, we realized that it was Outlook AutoDiscover. And we confirmed that when we started doing an investigation of the workstation. Now, I've not got confirmation back from Microsoft yet to why it's trying to Traceroute and why in the heck did they decide to use running in the payload for this. But for whatever reason, when Outlook is in AutoDiscover, it seems to try to do this Traceroute with these very, very weird ICMP echo request packets with running in the payload. Okay, so there's something else that's normal in my environment. But on top of that, we have other IT equipment. And in some cases, these IT equipment, there can be just a massive amount of things. For example, we've got monitoring systems, and some of them are really super cute. Have you guys seen them? Like SolarWinds, put SolarWinds Inc. in their payloads. And so some of them announce the payloads. You have storage systems, right? The controller or whatever device that's running your SAN environment or the disk arrays and tape libraries, they all want to make sure each of the devices is up, and they kind of ping themselves. Routers and switches are notorious for doing ICMP echo request type of messages. Actually, in this screenshot, this is from a Cisco router using IP SLA, which is a Cisco, it's built into iOS to do kind of latency performance measurements. And if you look, you can actually see kind of the pattern there. You see the ABCD. And in this environment, this one, if you look at the timing on the far left column, you can kind of see that it's every 3 seconds. So 0, 3, 6, 9, that's loosely 12, 15, 18. So you could help your networking teams out by helping them troubleshoot their IPSLA. Oh yeah, you've got that configured for 3 seconds to these IP addresses and whatever. So anyway, so that is normal behavior for this. But there's other equipment as well. Not only do we have IT equipment, but there are building systems like HVAC equipment. You've got generators and UPSs, physical security equipment that is now plugged into the environment, which funnily enough, I was actually doing some research on some network attached video cameras. And these video cameras actually weren't even using ICMP. We noticed that we were getting a bunch of drops in the firewall logs to DNS servers that were not approved external DNS for this environment, because everything needed to use the internal DNS, and then only the internal DNS servers were allowed to do recursion. So we went to the video cameras and was like, oh, we got to change this. Something must have happened with the DHCP or something of that nature. You couldn't actually change it. It was hard coded. So I reached out to the video camera company and was like, hey guys, I can't seem to change this. And they're like, oh yeah, you can't. That's how we're checking to see if the network's up. I'm like, why are you using DNS and not ICMP? And the engineer was like, because that's not what ICMP is used for. So I was like, oh, it's not? What's ICMP really used for? So that generated a whole nother long discussion. But anyway, just weird behaviors with building system equipment. And Internet of Things, right? Your toaster has got to be able to ping the toaster manufacturer for some reason, or your food services vendors. This one kind of gets to be frustrating sometimes, right? The business goes off and hires somebody to stock the food equipment, and then they start plugging equipment into your network. Because that never happens, right? But these are the normal things. We need to figure out what is normal in our environment, because there are a lot of command and control channel applications or data exfiltration applications, or an amazing number of things you can do that are abnormal to these ICMP protocols. There are a ton: Loki, ICMP Tunnel, Hans, ICMP TX, the PowerShell, the invoke PowerShell with ICMP SH, what's this say? Derek, Black Hills Information Security. If you go to BHIS's website, he's done a blog post if you are interested in seeing how to do that. But there are many, many others out there. I'm going to show you an example of P-Tunnel or Ping Tunnel, just because it's kind of very common and it represents how some of these works. A lot of them kind of use some sort of proxy potentially, or you can actually do a direct command and control channel. So in this case, P-Tunnel, so my client is 10.10.0.63, and I put IP addresses on here so you can actually follow along when we start looking at the packets. And I set up a P-Tunnel proxy somewhere out on the internet. So that's got to happen kind of prior to this command and control channel setup. And it's got a 100.14 IP address. And my client actually wants to SSH to 6921.118.164. Well, if you notice, the client actually never communicates to the server that it wants to SSH to. What happens is P-Tunnel sends in the ICMP echo request payload the SSH server commands, and then the proxy actually implements and establishes that SSH connection and sends the response packets back in the ICMP echo reply payload. Kind of cool. So if you're actually doing an investigation, you will never find 10.10.0.63 communicating directly with 6921.118.164. Covert channel using ICMP for something that it is not intended to be used for. So if you look at the packets, you can kind of see a pattern here. So again, notice that the first echo request has an ID of 61093 with a sequence number of 0, and then there's 2 replies. Now, I don't know about you, but I see a lot of times, you know, echo request or ping, 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 and no response, right? The site's not up, it's being blocked by a firewall. That's very normal. I have never seen a legitimate ping, reply, right? I should never get more than 1 reply to my ICMP echo request packet. And more importantly, if you think about how we've described how this is supposed to work, type 8 code 0, change the source and destination address, change the type to 0, code 0, and send the entire payload back. So notice that the second reply packet has got a different length. And you can see that in the second set. So the original echo request had a length, so this one's now sequence number 1, had a length of 916, and then there's a ping for 916 followed by a different length again, which is kind of strange. Well, what is happening is when your client, the 10.10.0.63, pings the proxy operating system is immediately responding, because that's what it's supposed to do, to the echo reply. So it's got a proper length according to how our understanding is. Well, in the meantime, it establishes that SSH session and sends a second echo reply with whatever's the payload of that particular session, which in this case happens to be an SSH banner. Oops. Now, you can, and there's several places where you can actually go find this. You can actually turn off the Linux default behavior of responding to the echo requests. So you would only have one reply. So you can make it a little bit stealthier, but you will still have different links and different payloads. So there's an indicator there. So we know how ICMP echo request and echo reply are supposed to normally work. We now have some way to look for indicators of suspicious, potentially malicious ICMP echo request, echo reply behaviors. So understanding what normal is so we can start looking for things that are abnormal, anomalies within our environment. Okay, so one more real quick, and on ICMP echo requests and echo replies, I know you guys are probably like, oh my gosh, this guy can talk forever. Yeah, I get it. So I just love reading RFCs. I know I am strange. I'm okay with that. Everybody that knows me says, yeah, he's strange. Just live with it. I get it. I like to read RFCs. And this is directly right out of RFC 792, which is details the ICMP codes and their messages and what they're supposed to do. And this is literally in the ICMP echo request, echo reply section. And I'm going to read it. It says, to form an echo reply message, the source and destination addresses are simply reversed. We got that, right? The type code changed to 0. Okay, we got that. And the checksum recomputed because we've changed it. We need to recompute the checksum. Okay, got that. Except for the type code changed to 0. The type code changed. Does that mean the type and code fields are to be changed to 0? Or are they saying the code in the type field is changed to 0? The type, So what do they mean by that? Well, we can test that. Now, if you think about it, there isn't any additional codes for type 8 or type 0. There is only code 0. But what if we had a way to maybe craft packets? And in this case, I'm showing SCAPI, which is one of my most favorite tools in the whole entire world. I am a huge SCAPI fan. Anyway, I'm showing here the first line says Linux_PKT. So I'm creating a Linux packet, and I'm creating it with a particular IP source and a destination IP address of a Linux host. And I'm setting an ICMP type of 8 and a code of 4. That doesn't exist. There is no type 8 code 4. Doesn't exist, okay? And then a payload of, I heart Linux, right? And then I'm creating a second packet called Windows_PKT and source IP of my system and a destination IP of a Windows device. And I'm setting its type and code to type 8 code 4. And then setting a payload for I heart Windows because, Windows packet. And then I send both of those packets. And in the bottom window, I'm using T-Shark in this case because I want to parse out some of the columns. So I've got source IP, destination IP, and then I have the type field and the code field followed by the payload. And T-Shark represents the payload in hex, so you can kind of see the I is hex 49. So capital I is hex 49 followed by the space, which is hex 20. So you can read the payload if you're interested. But notice that the Linux machine responded with the type 0 code 4. So Linux seems to interpreted the RFC as changing the type code to 0, changing the code of type to 0, and it didn't change anything else. Windows changed the type to 0 and the code to 0. So Windows seems to have interpreted as change the type and the code fields to 0 and reply back. So interesting enough, I get different behaviors based on these kind of odd ICMP packets. So with a single packet, maybe kind of correlate the initial TTL value and some other things, I've got a very, very cheap way to fingerprint operating systems. Interesting. Anyway, reading the RFCs sometimes gets interpreted differently by whoever the person is that happens to be reading it. So you will see kind of odd behaviors depending on how the person who wrote that code interpreted it. But there are other ICMP message types, right? IANA.org's got a really, really good list. I kind of cut a bunch of pieces out of that to show you all these different types and codes that go along with it. So we've got destination unreachables, we've got redirects, we've got, router advertisements, our time exceeded messages that we kind of talked about. There's all kinds of different other ICMP message types. And a lot of them have to do with the error reporting side of the ICMP role, not necessarily the simple messages piece. Now, RFC 6633 back in 2012 actually deprecated source quench, which was type 4. And then following the next year, so in 2013, RFC 6918 deprecated another 15 type ICMP type messages. So there's actually a bunch of these that no longer are official RFCs. But if you actually look at your protection devices, most of them still support these different types of messages. If you actually had firewall rules or some sort of intrusion detection or next generation firewall or some sort of configuration where you were responding to these, now that they're deprecated, what happens with those rule sets? Did your vendor change its behavior? Do you still have these rules, or are you still seeing this type of traffic? What is normal, and how do your host operating systems respond to it? If we look at the type 3 unreachable messages, there is a slew of these, and these are used a lot of times to try and elicit a response from a host to at least find out, is it alive, right? Can I get that host or that router or that device to respond? And if I can get it to respond, at that point, I now know at least something, right? I know the host is alive. In addition to that, if I can figure out, hey, maybe that protocol is unreachable, so I know it's not listening on that, or maybe that port is unreachable, can I reverse fingerprint it by seeing what all is not available to kind of determine then what is available? Again, based on, maybe a firewall configuration or some sort of prevention detection device that sits in between these systems. So how systems respond, I can use that for mapping and discovering activities in addition to the normal behavior of how a network's supposed to work, right? If your UDP port is not listening, you want the server or the device that's not listening on that service to tell that client, hey, stop trying, I am not listening on that, with a type 3 code 3 port unreachable type of message. Or type 3 code 4, fragmentation was needed, but the do not fragment bit is set. This is heavily used with path MTU discovery. So determining what the largest MTU is throughout a path, so I don't have to fragment the traffic. If this is blocked, I now no longer have that feature and potentially risk having to do fragmentation. Now, hopefully nowadays, most of us are at least 1500 byte MTU size, so this is a rarer case, but it is heavily used, especially within IP version 6 to do that path discovery. There's some other ways you can do it using TCP and stuff as well, but just be kind of careful about what these unreachable type of messages mean. They can be used to benefit the performance of your network, but they can also be used to elicit information and discover or map an environment unintended. Now, another thing I kind of want to point out about these error messages. So they have the similar format, type code checksum, and most of the error messages don't use the next 4 bytes. They don't use the second 4 bytes in that ICMP header. But what they do is add the IP header and 64 bits of the original datagram. So the thing that created the error message. The reason why ICMP does that is it's got to tell the system that created the packet that's not going to get delivered for whatever reason what is wrong. So that's what that IP header and the 64 bytes of datagram are, is it actually is telling the sending system, hey, whatever you sent is bad. Here's that packet that you were trying to send. So that's kind of cool, except for a lot of us have our devices sitting behind some sort of protection equipment, right? Next generation firewall, intrusion prevention system, IDS, whatever your load balancers, whatever's in your environment, right? Our things aren't usually directly exposed to the internet. So as a part of that, we use NAT. And again, not some people don't, but a lot of people use NAT, network address translation or port address translation, depending on which variety you're using, right? Use PAT. If I'm including in my error messages about the original packet, does my firewall or IDS, IPS, next generation device, load balancer, whatever happens to be there, does it know to NAT things inside my ICMP payloads? Oh, wait a minute. So some of this is masked out, but hopefully you can see that the source IP address is in the 6-something network range. But if you actually look in the error message, I'm leaking internal IP addresses by responding to this protocol request. Does your protection device update or mask the IP addresses that are inside the payload of this ICMP message? Or what about this? This is another example. Again, this was a scanner that was looking just for some protocol errors, and we got a protocol error. And notice at some point, and in this one, let's see, this one seems to be, I can't tell, in the 172 of some flavor, somewhere inside the internal network. And again, if you look, oh yeah, there it is. If you kind of look above that arrow for the bottom internal IP arrow, go up like about 3 or 4 lines, you see the time to live is 111. But if you scroll up, you can see the time to live of the real IP header is 127. So I've gotten 16 hops with inside this environment with this one message and got an internal IP address responded back. So this IP is somewhere inside that environment. Could I then maybe try to adjust TTLs to elicit some sort of error message to try and map those different hops with inside that environment and see, could I elicit more information? Are you allowing ICMP error messages? And if you do, are your firewalls scrubbing or natting or protecting you from potential information leakage? Now, something that's really cool, if you really want to search for this, Wireshark actually treats the embedded header as proper display filter codes. So if you'll notice here, I'm looking for an IP address that equals the 10 network, and notice that nothing on this page is from that 10 network. But if you click and drill into those, you will see all different 10 addresses that showed up as part of that scan. Kind of crazy, isn't it? So if you want, Wireshark will help you see, am I leaking any of this information? Do a packet capture from your external tap point and look, sort on your ICMP packets and then do a search for some of your internal address ranges, and are you leaking potential information out? Okay, so let's talk about some strategies, right? So prevention. Remember, our goal is prevention. We want to do some sort of preventative steps to protect our environment, but we've got to detect, right? So detection's a must. So let's talk through some prevention strategies first, and then we'll look at what is near and dear to my heart, which is the detection type of stuff. So for prevention strategies, look, you can just flat out say, hey, we are going to block all inbound ICMP messages. That's our stance. That's what we're doing. This is our stake in the ground. I am going to die on this hill. We are blocking them. And that is perfectly amazing and perfectly good for your environment. That works, right? Awesome. But just remember that you may be disrupting normal behaviors. Path into discovery, unavailable services. You may be impacting your networking team's ability to do troubleshooting. You also may be impacting their way to do service level discovery or some sort of SLA enforcement. So just kind of be careful with just blocking flat out. You also may get in trouble with your sales or marketing team. I work for an organization, and real loosely our slogan, motto, corporate policy was we were always available. We had to always look available to anybody who ever tried to connect to us. So we had organization requirements that required us to allow these messages, because no one could ever try to ping us and not get a response, because our motto was always up, always available. We needed to show it. So that's one. So that's another potential blocker for being able to just flat out and say block everything. So normally what I kind of like to try and do is recommend to, do some sort of selective inbound allow, right? So approved error messages, right? We allow path into you discovery, so we're going to allow those messages to come back in. Or we allow the networking team to do trace routes, so we're going to allow the time exceeded messages to come back in. We, at the company where we had to show always available, we actually set up a dedicated pool of servers that sat behind load balancers and stuff, and those servers were hardened, and all they did was respond to ICMP messages. So instead of allowing ICMP messages actually to get to our production systems, we just redirected those to this pool of ICMP messages, and then their sole responsibility was to respond to that. So that's a potential that you could do there. Again, you're not showing that you're up. You just happen to have a pool of servers that's what their responsibility is. For outbound, again, you can put the flag in the hill, and you can make a stance that I'm going to block all outbound traffic, and I guarantee you that's going to increase your support calls or your help desk tickets or whatever it is to your IT team, because every single person in your organization is going to try and ping their favorite website, and their favorite website's not going to respond to the ping, so the whole entire internet across the whole globe is down because they couldn't ping this site. You're going to potentially limit your troubleshooting, again, of infrastructure teams or your development teams, again, depending on what they're trying to do. You also may run into problems with vendor support, right? Office 365 uses new and interesting ICMP echo request messages for telemetry data. Maybe you want to block that. Maybe you don't. Maybe your food service vendor signed a contract with the business team that says they need to be allowed to ping their site or their offices or whatever it happens to be. You have to be careful with whatever your relationship is or whatever your contract is. You may be required to do that. So again, I usually recommend, again, if their policy can be they can block everything outbound, awesome, amazing, great, let's do that. But more realistic, most places need to allow some sort of outbound type of ICMP messages. And so you set up selective allow lists, right? So maybe your external DNS provider, you can ping those sites, or upstream ISP sites or something of that nature. And then train your user community to say, oh, did you try and ping this site? Oh, it works. Okay. So and kind of steer them down, practices that you would like to see in practice. And I've got a quick note in here. Just kind of be careful if you pick like your cloud hosted provider location address block, because it's not that difficult to spin up a malicious server in Azure or AWS or Cloudflare or anybody else. So just again, be careful what you allow on your approved list, and maybe not open it for everybody unless that's your policy, right? Your policy could be, look, we're going to allow ICMP messages. They're an important part of the networking community, and we want that to happen. So we're going to run through that. Okay, that's great. Well, then let's look at detection strategies then. So one is you can actually look for bad, right? We can take and we can look for SSH banners. We can and write some sort of signature to do that type of look for bad type of environment. That gets really difficult, right? It's easy to change a banner. The version number is going to change. I can put a space in there. It's kind of hard in this case to look for bad. But if you actually write pass rules for how it's actually technically termed for all of the known good, and then alert on everything else, That's a really powerful strategy, especially for signature-based detection. This one's really, really powerful. I kind of like that. And if you actually go to the SANS Blue Team GitHub site, they've got a list of rules that map some of these. Don't use the rules on this slide. I've kind of cut out some of the content so it fits on the slide, just to get the concept across. So these are very poor rules. Don't use those. Go to the SANS Blue Team GitHub site. That is a better location to find some of this. Flow data is absolutely amazing. I am a huge fan of flow data. Absolutely love flow data. This is coming out of Silk, but you can notice this is our p-tunnel covert channel, and notice that in the bytes column, we have a different set of bytes. Remember, our bytes should be the same. And we also have a different set of packets where we have more reply packets or type 0 code 0 than we have echo request packets. That's an anomalous behavior. So that is really, really, I mean, this sticks out like a sore thumb to me. I'm a huge fan of this. And you can actually see if you go down to, let's see, the last two lines there, 20 packets at 1200 bytes. So if I take that 20 into 12, 60 byte payload. So that 60 byte payload includes the IP header. So if I strip off the IP header, that's 40 bytes. Take off the 8 byte ICMP header, that's 32 bytes. So that is probably a standard Windows ping. So you can do some of that correlation really quickly with flow data. Flow data is amazing for this. I think these kind of weird anomalous activities stick out like a sore thumb. But you can also use Zeek, okay? So Zeek, look, you can write signatures in Zeek. Here's an example of writing a signature, looking for an open SSH banner type of signature, and this will detect that p-tunnel with that open SSH in the payload. But I'll be perfectly honest. Look, Zeek is amazing. I love Zeek. There are better products to do signature-based detection, right? Snort, Suricata, whatever your IDS for your enterprise is, those, assuming you can write rules for your enterprise IDS, right? Okay. Those are better products to do signature-based detection. Again, and this is a very simple rule. You could make this kind of a lot more elaborate. I just prefer to use a tool with a better signature-based language to do my signature-based detection. You can also use Zeek for doing some similar things like the flow, right? So this is out of the Zeek conlog, and you can pull the data and see those differences. You can see the differences in your packets and your bytes, and pull the data out of the conlog. Which again, this is really, really powerful. And a lot of people do this. They'll take and they'll ingest these conlogs into their SIM tools and work through that. But for me, the actual power with Zeek is in the ability to look for anomalies. And the reason is when Zeek writes to a log file, that's when the connection ends, okay? And if I've got a large exfiltration of data going on, I don't want to know about it when it ends. I want to know about it when it's happening. I want to correlate that activity while it's going on, or a very long ICMP connection, or mismatched payloads, or different numbers in echo requests and replies. I don't want to wait until it's done for my service to ingest it and then tell me about it. I want to know when it's going on so I can respond and react to that. That for me is the real power of Zeek. So this is a very, very simple Zeek script. Again, this could be cleaned up a lot before going into production, but what I wanted to show you is this, everybody can do this. Don't be scared of trying to write scripts with Zeek. It looks very programmery. I'm not a programmer, but I can do this, okay? Yeah, look, I'm using black background with white lettering and screenshots. You don't want me designing UIs or programs or anything of that nature, right? But I can write these scripts. It is very, very readable and approachable by most people. So in this case, all I'm doing is I'm setting a global variable, it's a set variable, and I'm taking three things in it, a string, a count, and another string, and then I'm saying if something was added into this variable, expire it out after 4 seconds. So what I'm going to put in here is I'm going to put a unique identifier that's part of Zeek. I'm kind of already running over, so I'm going to kind of go quick. But the unique identifier, it uniquely identifies that particular connection within Zeek. It's a Zeek field. And then I'm going to put the sequence number in the payload, because I want to match the sequence number and the payload and see, do they match? So that's what I'm going to add in there. Now I'm expiring it every 4 seconds, because if you've not gotten a ping response or an echo reply within those 4 seconds, just delete it, right? Either you've got a really, really bad network and you need to hire better network engineers, or you're never going to get a response. And it kind of keeps it, system performance a little bit better. That could be an arbitrary number. Again, there is a lot of tuning you can do with this script. I just wanted to show you the power of doing this anomaly detection. And then what I'm doing is I'm subscribing to the ICMP echo request event. And what I'm doing, basically you cut and paste that off of Zeek's website. So literally you can Google Zeek ICMP echo request, and it's going to show you exactly what's in the parentheses. You cut and paste that in your script. You don't need to do anything with it. And then you put your braces or your squiggly brackets, depending on what you call them. And then I'm just saying, in that, when you see an ICMP echo request, add that UID, sequence number, and payload into that variable. And then I'm subscribing to the ICMP echo reply event. So now when I see a reply, if those 3 items are in the global variable, in the ICMP check, just return. I'm done. There's nothing else I need to do, because that matches, which means it's a valid ICMP echo request and reply. If they're not in there, print out a message that says, hey, there was something suspicious that happened between these hosts, and that end thing is just saying, give me the length of whatever the payload is. That's it. So whatever this, what is that, 10 lines or something, that's all there is to doing this anomaly detection within Zeek, to check for echo replies that have a different payload than their echo request. That's it. That's all there is to this entire script. And then if you run that, in this case, I'm running it against just that static data, but you could load this. Actually, you want to tune it before you load that script into a production environment. But you will see, as soon as it starts seeing that anomalous behavior, it's sending me messages. It's not waiting until the connection is done and then me ingesting or diving into those con logs. This is actually reacting as it sees those events and passes it through. And then it obviously prints out to the con log, and this is just a very similar slide that we have from there. Okay. I know I talk a very long time. I apologize for taking you 7 minutes over. Thank you very much for hanging in there with me. If anybody has any questions, please feel free to type them into the question and answer board. Otherwise, thank you for joining me. Feel free to reach out. And Jessica, at this point, I don't see any questions.
All right. Well, thank you so much, Andrew, for that great presentation. If there's any unanswered questions that you would like to have Andrew answer, you can always send them to q@sans.org. And with that, thank you, Andrew, again for that great presentation, which helps brings this content to the SANS community. To our audience, we greatly appreciate you listening in. For a schedule of all upcoming and archived SANS webcasts, including this one, please visit sans.org/webcast. And yes, there will be a recorded version of this session. I'm looking at the questions right now, and it is available for download. Until next time, take care, and we hope to have you back again for the next SANS webcast.